So what are these intermolecular forces? There's three different kinds. That's not what I wanted. There's the dipole-dipole forces, there's hydrogen bonds, and London dispersion forces. And we will talk about what these different things are. But all of them are electrostatic in nature. Electrostatic means attractions between opposite charges. So this attraction between opposite charges acts in much the same way that magnetism does. And so you can think of these in terms of magnetics, the little toys where the balls and sticks are sticking together because they're magnetic, or Brio trains where the little trains stick together. As the molecules get farther apart from each other, those forces become weaker. And you think about two magnets. When they're really close together, they pull together really strongly, don't they? But when you pull them apart, the force gets weaker and weaker. And when you get them, maybe even just an inch apart, you don't feel any force of attraction between them at all. So that force of attraction depends on the distance between them. So as they get farther apart, they get much weaker. Much, much, much weaker. So let's talk about dipole-dipole attractions. So, we talked way back when about polar bonds and polar molecules, right? And we said that a polar molecule is one that has a slightly positive end and a slightly negative end. So this is just some generic illustration of a polar molecule. So this end's a little bit positive, that end's a little bit negative. This slightly positive end is attracted to the slightly negative end of a neighboring molecule. This is not an ionic bond. An ionic bond, you have a full +1 charge and -1 charge. This is a partial charge, a little teeny tiny charge. And so it's just a very, very small attraction. And yet if you get a whole bunch of them, they become significant. So here is an illustration of a liquid. And so you have forces of attraction between opposite charges and forces of repulsion between like charges. And the dipole-dipole attractions can be enough to keep that substance as a liquid instead of letting the particles fly away from each other as a gas. Question?
So with those, once they're in something, like a liquid, as in that same structure, would they kind of relatively stay in like the same places, or would they?
That's a good question. So here, as a liquid, are these going to be kind of fixed in position, or are they going to be moving about? As a liquid, they'll be moving around. If it's a solid, they'll be fixed. And so, well, what's the difference between a solid and a liquid? Well, all of these particles have some kinetic energy. They have movement. Okay, we talked about the difference between solid, liquid, gas before. So right now, you guys, you students, are in the solid state. You're sitting in chairs and your positions are the same relative to each other, and yet you're moving, right? You're breathing, you're shifting, you're taking notes, you're checking Facebook, whatever. So you're moving. And the warmer the temperature of particles gets, the more they move. And so you get more and more agitated until finally you just can't sit in your chair anymore, and you get up and mill about the room. And that's a liquid. So if there's enough kinetic energy, then they will be able to break these little forces of attraction and move around. But as soon as it breaks one, it's going to form another one. And so they're allowed to mill about, but they can't fly away from each other in the gas state. Question?
It's just kind of off. Would polar liquids naturally be more dense than non-polar liquids?
That's a good question. Would polar liquids be more dense than non-polar liquids? There's other factors that are more important than whether they're polar or non-polar. More to do with the mass and the relative size. But that's a good question. The polar and non-polar molecules are going to have different types or different strengths of intermolecular forces, and it does affect a lot of their properties. So if these are in a solid state, then they're going to be fixed relative to each other. And so at a low thermal energy, a low kinetic energy, it's going to freeze, and they're going to be solid. As you warm it up and they get more and more agitated, they get enough energy that they can break some of these and they can slide around next to each other. So those are dipole-dipole forces. Those are attractions between polar molecules. So dipole moment, molecules that are polar have polar bonds often behave in an electric field as if they had a center of positive charge and a center of negative charge. And if you have molecules with dipole moments, they can attract each other. So they've got a positive end or negative end. This is only about 1% as strong as a covalent or ionic bond. Okay, so these forces are very weak. They're very weak, really weak. So 1% is strong. So a covalent bond is 100 times stronger than these. So these can be broken pretty easily by movement. One way to think of these intermolecular forces, temperature. So you can think of it as Velcro. Okay? So if you've got people walking around and they've got Velcro, and then you rub past someone and it kind of pulls at you, right? And so you can get stuck to each other. How do you get apart from each other? You have to exert some energy to pull away. And that usually involves a jerking motion, right? So if you're moving fast, then you're not going to stick together as much as if you are moving slower. So when they have more thermal energy, they have more energy to break those forces of attraction. Another one is hydrogen bonding. Now, hydrogen bonding is actually a subcategory of dipole-dipole forces. So these are just like dipole-dipole forces on steroids. Okay, these are super strong. Superhero dipole-dipole forces. Maybe that would be better. Steroids are bad. Don't use them. Not worth it. So when do we have hydrogen bonding? We have hydrogen bonding when we have hydrogen that is attached to one of the highly electronegative atoms. So nitrogen, oxygen, or fluorine. And so one way to remember this is, did you ever see E.T.?
Yes.
E.T. phone home, right? F-O-N-H. So if you have fluorine, oxygen, or nitrogen bonded to hydrogen in a polar molecule, that molecule is extrapolar. And so those electrostatic attractions between the positive and negative ends are extra strong. So you have to have hydrogen bonding, right? Hydrogen bonding. Okay, and it's kind of misleading to say bonding because it's not a covalent bond. It's just an extra strong intermolecular force. It's still much weaker than a covalent bond. But you have to have hydrogen. The hydrogen has to be bound to fluorine, oxygen, or nitrogen. Otherwise, you can't have any hydrogen bonding. So here's an example of hydrogen bonding in water. Water's a polar molecule, and it's got hydrogen-oxygen bonds. That's one of the elements. And so the result of that is, because oxygen is one of the most electronegative elements, and hydrogen is this poor little guy, that this ends up being an extrapolar molecule, and the negative charge on oxygen is greater than it is on something like dihydrogen sulfide or something, H2S, because sulfur is not as electronegative. So the partial charges here are larger than on most polar molecules. So we've got a larger negative charge here and a larger positive charge here, and so then the amount of attraction is greater. So the hydrogen bonds are represented by these dotted lines. These are bonds, covalent bonds between hydrogen and oxygen atoms, and the dashed lines are this interaction, this attraction between the molecules. Any questions?
So why is this explaining why the hydrogen won't go to the other hydrogen on the water molecule? Or
Well, the hydrogen, this hydrogen is not going to be attracted to another hydrogen because they're both slightly positive in charge. And same like charges repel each other. But it will be attracted to the oxygen. So we were talking earlier about how water's less dense, ice is less dense than water. When water freezes, it arranges in a way to maximize this hydrogen bonding. And that's why it makes this open structure. It really has to do with the hydrogen bonding.
so why is it that the hydrogen bonding is stronger?
Because it's only when we have oxygen, fluorine, or nitrogen here. Those are the three most electronegative elements. Fluorine's the most, oxygen is next, and nitrogen is next. And so these bonds are more polar than most polar bonds are. And so the partial charge here is greater, and the partial charge there is greater. And that force of attraction depends on the size of the charge. So higher charge, stronger attraction. It's still not as strong as an ionic bond, though. Any other questions?
Because hydrogen's weird.
Well, because hydrogen is small and it's not very electronegative. It doesn't have very much attraction for for the electrons in that shared bond. It only has one proton. It's just not much attraction there.
That's what I'm getting confused on. Is
Why hydrogen?
Why hydrogen would be a stronger, why the hydrogen bond would be a stronger force than the dipole force, even when there's less electrons, right, for hydrogen, because it has nothing to do with electrons.
Well, it does have to do with electrons.
I can understand why. Okay, I can understand the nitrogen, oxygen, and fluorine.
Let me look something up.
But I don't understand why the hydrogen is.
Well, it has to do. Did we talk about electronegativity? I don't even remember.
Yeah.
Good, because we should. Electronegativity.
Was that the iodine?
So hydrogen.
Is that where it's closest? Yeah.
Yeah, fluorine. Yeah, so hydrogen is 2.1, and nitrogen, that's a 3. That's not an N. Nitrogen is 3.0. We've got oxygen, and fluorine is 4.0. I think oxygen is 3.5. So we have a nice amount of difference between these. So that's an electronegative. A difference in electronegativity. This is more polar than like if we have hydrogen and sulfur. Sulfur is only 2.5. So a sulfur hydrogen bond, the difference here is 0.4. That's right on the borderline between being considered polar or nonpolar. Whereas these bonds of hydrogen with nitrogen, oxygen, fluorine are all very polar bonds. And so that means the electrons, because there's a greater difference, that means the sharing is very unequal. And so in a hydrogen-nitrogen bond, there's 2 electrons, but they spend a lot more time around the nitrogen than they do around the hydrogen. So we have this partial positive charge here, and where to write it? Partial negative charge over here. This partial negative charge is larger when the difference between these two, when the difference in electronegativity is larger. The partial charge is larger. It also plays into it, I believe, that the hydrogen is such a small atom. I think that has something to do with it, but that's getting beyond the scope of what even a 3A textbook talks about. But it's the unequal sharing. They share very unequally. And so this charge is getting closer, this charge is getting closer to a negative 1
Is it
charge.
kind of like it's harder to take a small piece of lint off of a shirt out of a dryer rather than like a larger piece of something? When they're attracted? Is that what you're implying by the size?
Just because you can't keep it up.
No, I don't think so. I really don't want to emphasize the size with the hydrogen thing. I think the best thing is to emphasize the charge here. So like if this was, I'm not saying it is, but if this was maybe a minus, where to write this? If this was a minus 1/2 charge, and for the nitrogen, and for this one maybe it was a minus 1/16 charge because of the spread of the unequal sharing. Minus 1/16 and plus 1/16 are not going to be as attracted as strongly as minus 1/2 and plus 1/2. Does that make sense? We don't do Coulomb's law,
Because
but
the greater difference, the more polar. The greater the polarity. Is that right?
oh wait, that's not right. The greater the difference in electronegativity, the greater the polarity. There's something called Coulomb's law, and the force of attraction equals the charge on one object times the charge on the other object divided by the distance between them squared. That's the force of attraction between two charged particles. So if these Q's are larger, then the force of attraction is greater. If the Q's are smaller, the force of attraction is smaller. And so because the difference in electronegativity is greater between hydrogen and nitrogen, oxygen, fluorine than it is between hydrogen and other things, or between pretty much any other elements, then you get this larger charge and you get this stronger attraction. Okay? So hydrogen bonding affects physical properties. So this is a diagram, a graph of the boiling points of the hydrides of group 6A. So if you look at the periodic table, oxygen, sulfur, selenium, and tellurium are all in the same column. They're in group 6A. They belong in the same family, and they will form compounds with hydrogens where there's two hydrogens and one of these group 6 elements. So H2O, H2S, H2SE, and H2TE. They form the same type of compound. And if we graph the boiling points of these, tellurium has a boiling point that's just below 0 degrees Celsius. H2SE looks like maybe minus 50 degrees Celsius, and hydrogen disulfide, which is a gas at room temperature, all of these has a boiling point, looks like maybe, I don't know, minus 70 degrees Celsius. And this trend usually is going to continue, and we would predict the boiling point of water to be down here around minus 100 degrees Celsius.
Why do you say the boiling point if it's under 0 degrees?
Well, it'll boil at minus 100 degrees Celsius. Well, or at minus, 75.
Oh, because they're...
So if you had it cooled down to like minus 200 degrees, and you warmed it up, it's a liquid, and then it'll get to its boiling point and it will boil. So there are things that would boil in your freezer. Okay, kind of weird to think about, huh? Right? Yeah. Yeah.
Because no one could ask some questions about minus degree, and I'm like, what the heck is that?
Yeah, it's just kind of this mental barrier you have to get over. But why? Why does water boil at plus 100 degrees Celsius? Because.
Just because.
Well, do these other compounds have hydrogen bonding?
Yes.
Do they have hydrogen bonded to phone, F-O-N? No, they don't. These are all polar molecules. They have dipole-dipole forces. But hydrogen bonding is much stronger. So what happens when something evaporates? It takes more energy. Mm-hmm. So water, having the hydrogen bonding, those guys are really sticky. Their stick-togetherness is high. They're just really sticky. And so in order for them to get away from each other and go into the gas state, it takes a lot of energy. And that is related to a higher temperature, because temperature is related to kinetic energy. These other compounds, they have dipole-dipole forces, but those are much weaker. And so they're just really not sticky at all, and you warm them up just a tiny bit and they just fly apart. They just do not stick together well at all. Okay? So the strength of the intermolecular forces affects physical properties like boiling point and melting point. Stronger intermolecular forces mean that the freezing point and the boiling point are going to be higher because you have to have more energy to break out. Okay? Does that make sense?
Yes.
Good. Okay, we're out of time. We didn't finish London dispersion forces. We'll do that on Friday.